most people don't actually use the non-parametric RBF, even though it's great, simple, and so on and so forth, because of those computational demands. Actually, when people refer to the RBF, the radial basis function, they're typically referring to the parametric radial basis function, which we're about to derive. Now, in order to appreciate the differences, it's going to be helpful to look a little more carefully at the non-parametric RBF. So let's do an example by hand. So I'm going to draw some data. Okay, and imagine. So we're always going to be working with the Gaussian kernel. Okay, and so I'll draw 3 data points. Okay. And let's see when r is very, very small. So r, let's say small, is approximately 0. For example, 0.01. Okay, so r is very, very small. So here's x and here's y, and we're doing regression. Okay, and let's see what the final hypothesis looks like. Okay, so let's derive it by hand. Now, the nature of the Gaussian kernel is that it's dropping as your test point gets further and further away. You're going to have e to the minus of this distance squared, and then e to the minus a slightly larger distance squared. Okay, and the nature of that Gaussian scale is that when you square, okay, you pronounce the difference. Okay, and so the ratio of this weight to that weight will go to 0. So as you move further and further away from your data, the non-parametric RBF basically takes on the value that's the value of the closest data point. Okay, so it's converging to some value over here. Okay? And the same thing, it's converging to some value over here as you move to the extremes. Okay? And then as you get closer to the data, it starts, approaching this value. I mean, it converged to that value, but now it's starting to go up as this data point starts having some influence in the average. Okay, and because r is very, very small, it's gonna pretty much stay close to this guy until about halfway, at which point this guy pretty much takes over. So very quickly, and then it's going to stay at that guy pretty much till halfway, and then this guy is going to take over. Okay, and it's going to converge, and that's pretty much how it's going to look. Okay? So by hand, we've analyzed, for this simple example of 3 data points. Now let's see what happens if you increase r. So you increase the scale parameter. So I'll draw the same data. Okay, and you've got your 1, 2, and 3 data points. Okay, now again it's the same. Okay, even though you've increased r, but as you get further and further away, you converge to the value of this guy. We're doing regression. Okay, so the average of the weighted average is just the value of this guy, because this guy's weight becomes humongous in comparison to the other 2 weights. Okay, so again you're going to converge. You're going to converge, but now because r is larger, so let's remind you that r is large. Now, because r is large, you start rising. This guy starts having an influence earlier, and so you'll start rising earlier. And this guy will still continue to maintain an influence even as the test point approaches this guy. So it's going to look something like this. This guy will be influencing, okay, and then it's going to look something like that, and it converges to that guy. Okay. So it smoothens it. And if you choose r very, very large, then basically you'll still get the convergence on those 2 ends, but then it'll more or less be the average around here. Okay, so that's the non-parametric RBF for this simple example. Now, I want to show you the parametric RBF. Okay, and it just boils down to looking at this final hypothesis in a slightly different way. So here's what I'm going to do. I'm doing nothing. I'm just rewriting. Okay. So g of x. So we're deriving the parametric RBF. Okay. So I'm just going to rewrite g of x is equal to the sum from n equals 1 to big N. So, now let's look at this term. Okay. This term is alpha n of x, x. Okay. And we viewed this earlier as the weight of data point x. The weight of data point xn. Okay, but now I'm taking the alpha n of x out and I'm putting this yn here, okay, divided by the sum from m equals 1 to big N of alpha m of x. And I'll just remind you what is alpha n of x. This is equal to the sum from n equals 1 to big N of, yn divided by the sum over m, alpha m of x, so it's this term, times phi, your kernel, at, x minus xn divided by r. Okay, and now, you know, this function phi is symmetric. So here, when I was doing the nonparametric RBF, I was viewing, you know, this phi as a bump that's centered at x. Okay. It's also convenient now to view this phi as a bump centered at xn. Okay, so a bump. Okay, so you have x here, and you have xn. Okay, and now you can view this now as a function of x, keeping xn constant. Okay, so it's a bump, okay, centered at xn and dropping. Okay, and it's the same bump, it's the Gaussian kernel. Okay, and the contribution of this point to x is equal to the bump's value, okay, which used to be called alpha n of x, okay, times this quantity. Now let's call this quantity Wn of x. So this is equal to the sum from n equals 1 to big N of Wn of x phi of x minus xn over r. So I'm viewing this as a bump at xn. Okay, the bump at xn by the symmetry argument has exactly the value alpha n of x at x. Okay, but the contribution of this point to the weighted average is this guy multiplied by Wn of x. Okay, so what is that equivalent to? That's equivalent to raising the height of this bump. Okay, so multiplying this bump by Wn of x. Okay, so now I will instead of having the standard phi bump, I can think of placing another bump, okay, which is, you know, the phi bump, okay, but weighted. Okay, so I increase the height by Wn of x. Now, why do I say increase the height and make it a height Wn of x? Because this guy, when this argument is 0, is the Gaussian or a typical kernel evaluated at 0, will be 1. So I instead of having a height 1 bump, I have a height of the bump given by Wn of x. Okay, and then I look and see what's the contribution of that bump to this point. Wn of x. And if I had another data point, let's say another data point xm here, okay, so then it has a different way, it has a different height, Wm of x, okay, and so I compute this guy, okay, and now I get this contribution plus, you know, this contribution, okay, I add those two up and I get g of x. Okay, so another way of viewing this final hypothesis g of x is as a set of bumps of different heights at all the various data points. So I place a bump at each data point, and then each data point's bump, you know, decays gradually until it gets to x, and I have a contribution from each data point for the corresponding bump, and I add them all up. Okay, so that's another way of viewing this final hypothesis. But now I'm going to make a slight approximation. You know what? You know, I don't need these heights to depend on the test point. Okay, so let me fix those heights once and for all. Okay, in which case these heights become constants. So fix these heights once and for all. So fix the heights. Okay, and now my final hypothesis becomes g of x is equal to the sum from n equals 1 to big N of Wn, some constant fixed heights, times phi of x minus xn over r. End of story. This we call the parametric radial basis function. Parametric radial basis function. Okay, and so what's going on here? Okay, so let me draw another picture. Okay, what's going on here? Okay, we've just adapted this picture now to the case where the heights are fixed. So you can think of it now. I don't really have a test point anymore that I'm interested in. Okay, I have, you know, a bunch of data points. Let's call them, you know, the x values of the data points. Okay, I put a bump on each of these of a particular width. Okay, so this is the scale parameter. So I put a bump here of a certain height. I put a bump here of a certain height, same width, maybe higher. I put a bump here of a certain height, same width, but maybe a little bit lower. And I put a bump here of a certain height, Okay, same width, maybe much higher. Okay, so I put 4 bumps, and each of them have heights. Okay, now this looks a very intuitive, way to build a function. So each of these has a height Wn. Okay, and now, basically at any point, at any test point, I take the sum of the contributions for each bump. So in other words, if you view these as functions, my final hypothesis is just the sum of these bump functions. I'm going to get something like, for my final hypothesis, I'm going to get something like, going down, okay, but now I get the contribution of 2 bumps, okay, and now, the other bumps contribute more or less nothing when you're very close to this data point, okay, and then these 2 bumps might contribute, okay. And it goes back up, okay, down, maybe this comes down to here, okay, and then there. Okay. So, the nonparametric radial basis function, viewed from another way as bumps placed on each data point of a particular height, but that height depends on the test point. Okay. Now, I make the small approximation that, I don't want to change the height with respect to each test point. I'm going to set the heights, fix the heights once and for all. Now I have a bunch of fixed bumps, okay, at each data point. And so when I look at the resulting function, it's basically a very similar function, except that the heights are now fixed, and that corresponds to this picture. Okay. And then the only question that remains is, how do I pick the heights? How to pick the heights? Okay, how to pick the heights, the fixed heights of each bump centered on each data point. Okay. And here's the basic idea. Look, okay, so now, I'm putting these bumps of particular heights, but then we also have the y values. So the y values are, given to us. Maybe these are the y values. Okay. So these are the y values. Let me shade them in, just to show you my ability to color circles. Okay, so these are the y values. So, simple, task, vary the heights of the bumps so that you predict all the y values correctly. And do we expect that to be possible? Yes, because we have 4 y values to predict, and we can vary 4 bump heights, and we can vary those bump heights independently. So we have a lot of power in terms of, setting the various bump heights, okay? And so we should certainly be able to, manipulate the bump height so that we accomplish the correct y values for the data. Outside the data, we don't know what's going on, but for the data, we should be able to accomplish the correct y values. Okay, and so that's the basic idea. And so we'll come back and we'll see how to do that. Okay, so let's see what the parametric RBF looks like for our little example, where we now fix the height of the bumps on each data point, but we choose those heights so that we can fit the data. Okay, so here's, first data set here. It's the same data set twice. Okay, so I'll repeat the data set again. Okay, now what determines the width of the bumps is the radius. So when the radius is thin, the bumps are very thin when the radius is small. So the bumps, so there's a bump centered at this point. Okay, so here's an x value, here's another x value, here's another x value. So there's a bump centered at this point, but it's very narrow because the scale parameter is tiny. So if it's very narrow, then the height of that bump, so this bump will contribute basically only to this function value and won't contribute to the others. So the height of that bump will have to be almost the same as the y value for that data point. Remember, the y values, by the way, can be positive or negative. I'm just illustrating here with all positive. If the y value was negative, the bump height can be negative. Okay? So this guy will look, there'll be a bump here. Okay, there'll be a bump here. Let's say, very narrow bump. And then there'll be a bump here, not a very narrow bump. Okay, and so when you add up these bumps, what's the function you implement? You implement this guy. which basically gets, all your data correct, but it does so in this very, peculiar way with very thin, sort of almost like delta functions, okay, at each data point. Okay. Now, what happens when your radius is large? So now the bump, you still place 3 bumps, but now we get to choose the bump heights so that we fit the data. Okay, so this guy will have, a bump that's quite wide. Okay, this guy will have a wide bump. This guy will have a wide bump. Okay, so 3 wide bumps. And now you see that each bump contributes all over the place because they're wide, because R is large. Okay, the scale parameter is large. And then when we add up these bumps, okay, it's necessarily going to be the case. We've chosen the height so that when you add the three bumps here, you reproduce that data point. When you add them here, you reproduce that data point. When you add them here, you reproduce this data point. So it's going to look something like, we're going to go up to this guy. Okay, then this starts dropping, but that starts increasing. So maybe it'll look something like that. It'll come up to this guy, and then this starts dropping, and meanwhile that starts increasing. So, but it'll eventually drop down to that guy. Okay, and then it'll smoothly, okay, and you get a much smoother looking fit to the data. So, how wiggly the fit is depends on the radius, but you might wonder, does that mean we've overfit? Well, it turns out that in both cases we have the potential to overfit, because in both cases we're guaranteed to fit the data because we have enough bumps. We have enough parameters. We have 3 heights and 3 points to fit. Okay. Now, of course, you don't do this visually, or by hand when for the d-dimensional general case. So let me show you exactly what's going on. Okay. So what we'll do is we no longer need these pictures. So let's erase. Okay. I'll rewrite the parametric RBF, so parametric RBF, so g of x is equal to the sum from n equals 1 to big N of wn phi of x minus xn divided by r. Okay, and these are parameters now where we set these bump heights. Bump heights are parameters. Okay, and how do you actually set the heights? Well, we want to solve. Okay, we want to solve for w1 up to wn. And what do I mean by that? Well, we want this function to reproduce the target values at every data point. So we want g of x1, which is the sum from n equals 1 to big N, wn phi of x1 minus xn over r to equal y1. And we want g of x2 to equal the sum from n equals 1 to big N, wn phi of x2 minus xn over r to equal y2. And so on, g of xn is equal to the sum from n equals 1 to big N, wn phi of xn minus, this is big N, sorry, this is big N. X big N minus x little n over r to equal y big N. So we have to just solve this system. This is a system of n equations in n unknowns. Okay, we can solve, and that's basically how you fix the bump heights to fit all the target values. Okay, but now let me put this in a much more familiar form, because look, the parameters that we're trying to set appear linearly in the hypothesis. Okay, and so what's going on here actually is, you can think of this is basically a linear model. So this is a linear model. Okay, and what are the parameters? There we have the weights. Okay, we have weights W0, W1, W2, and so on up to Wn. Okay, and we need to fit the weights to the data, and we need to fit the weights to the data. Okay, so let me define a feature transform. Okay, let me define a feature transform, which is mapping x to z. So I'm going to define a feature transform that maps x to z. Okay, and what is z? So z has n features, so it's an n-dimensional feature transform, z1, z2, z3, and so on up to zn. So z is an n-dimensional feature transform. And what is this n-dimensional feature transform? Well, what's the first feature? The first feature is phi of x minus x1 over r. Okay, and the second feature is phi of x minus x2 over r. And the third feature is phi of x minus x3 over r. Okay, and so on, phi of x big N minus x, of x minus x big N over r. Okay, this is an n-dimensional feature transform. Okay, so the kth feature is the kernel applied on x minus on the distance to the kth data point. Okay, so you can think of these as similarity features. Similarity features. Okay, and so when I get a test point x, I compute its similarity to the first data point, its similarity to the second data point, third, fourth, and so on up to the nth data point. So I've computed n similarities. Okay, and that gives me n similarity features. Okay, and now I'm just running a linear model with respect to these n similarity features. So it's an interesting little twist on the concept of a feature, whereby the features are defined. What are my features? They're defined by my data, but that's perfectly fine. Okay, I can define these features ahead of time as I'm going to compute the feature transform, which is what are your similarities to the various data points, all n of them. Okay, and that's going to give me my feature vector for any x. In particular, I can compute my feature vector for the training points. So I can compute, z1, which is, the feature vector phi of x1 minus x1 over r. So that's going to be phi of 0, which is 1. So, the first data point has a similarity of 1, the maximum with itself. Okay, phi of x1 minus x2 over r, and so on. Phi of x1 minus xn over r. Okay, so I compute all the similarity features for data point x1. And similarly, all the similarity features for data point x2 and all the way up to xn. Okay, and now I can collect all of those in a matrix. Okay, so let me erase. So now I can collect all of these features into a matrix Z, okay, which is Z1 transpose, Z2 transpose, up to Zn transpose. Okay, and I have my y values. Y equals y1, y2 to yn. Okay, and this system of equations is exactly the system zw equals y. I want zw to approximately equal y. Okay, and I can solve this problem for classification, for regression, or for logistic regression, where my data matrix is given by z and my target vector is given by y. Okay, and if it's regression, then w ln is equal to z pseudo inverse y, which is z transpose z inverse z transpose y. What are the dimensions of z? So what are the dimensions of z? I'll give you a couple of seconds, and if you're coming back just for the ride, okay, pause the video. If you pause the video and said that z is n by n, then you're correct. Z is a square matrix, so z transpose z inverse will typically always exist. Okay, and if you're doing regression, then you solve using the pseudo-inverse algorithm. If you're doing classification, you have your data in your feature space Z and Y, and you can run the PLA or pocket. Okay, if you have your if you're doing logistic regression, you have Z and Y, and you do gradient descent. Okay. And so this is the nice thing about the radial basis function, the parametric radial basis function. It reduces to a linear model with similarity features. Okay. Now let's address the one final deficiency, which is, let's take the case of regression. When we take the case of regression, what's the final deficiency? The final deficiency is that, well, we have way too many parameters. We are guaranteed to fit the data exactly. So we have way too many parameters, overfitting. Way too many parameters. That means overfitting. So we need to figure out how to deal with that. Okay, so let's erase, and when we come back, I'll introduce you to the parametric radial basis function network, and that's our final radial basis function model, and that's the one that people normally use.